Forces holding things together, the invisible links between particles. What if they're far stranger than we ever imagined? Welcome to the Deep Dive. Today, we're jumping into, well, the really deep end of quantum physics. We're looking at two incredibly profound and, frankly, pretty puzzling phenomena: the Quark-Gluon bond and quantum entanglement.
Yeah, and these aren't just, abstract ideas for physicists. They really dictate how to the cutting edge of quantum information science. It might actually lead to a whole new view of reality itself.
Okay, let's start there then, with the strongest grip in the universe, the Quark-Gluon bond. You said it's not just a force, it's the most powerful one we know.
Yeah.
Holding protons, neutrons, all that stuff together.
Exactly. It holds hadrons together, and it comes directly out of a theory called quantum chromodynamics, or QCD for short.
Sure.
And QCD is, well, it's a pretty sophisticated quantum field theory. The really unique thing isn't just positive or negative charge, like, in electromagnetism. Quarks and gluons have something totally different. Color charge.
Color charge. You mean like actual red, green, blue? That sounds, well, very visual for quantum physics.
It does, yeah.
Yeah.
Red, green, blue, and their corresponding anticolors. And this whole idea of color charge, it was actually vital for solving a big puzzle. There was this particle, the delta plus plus. It has 3 identical up quarks, all spinning the same way. That should violate a basic rule, the Pauli exclusion principle.
Because identical particles can't be in the same state.
Precisely. But if each up quark has a different color charge, one red, one green, one blue, then they're not identical in every way. Suddenly it works. Color saves the day, basically.
So the colors make them distinguishable. Okay. And you mentioned that particles we actually see, like protons and neutrons, hadrons, they have to be colorless or white.
That's the rule, yeah. Color neutrality. So in baryons like protons, you get 3 quarks, one of each color, red, green, blue, mixing to white. Or in mesons, you get a quark and an antiquark pair, like red and anti-red, which also cancels out to white, always balanced.
Makes sense. And this force, it's carried by particles called gluons.
Correct. There are 8 different types of gluons, which comes directly from the underlying math of QCD, the SU3 symmetry group. But here's the really critical bit, the thing that changes everything compared to, say, photons in electromagnetism.
Okay.
Unlike photons, which have no electric charge, gluons do carry color charge themselves.
So they're not just messengers passing the force along.
Yeah.
They're actually part of the interaction. They can interact with quarks, sure, but also with each other.
Exactly. That gluon self-interaction is the absolute key. It's what gives the strong force its totally unique defining features. Features you just don't see anywhere else, like asymptotic freedom and color confinement. These 2 properties really set it apart.
Right. Asymptotic freedom. That sounds completely backwards. It means quarks interact less strongly when they're super close together, like at high energies.
It is totally counterintuitive. They almost act like free particles when they're crammed inside a proton.
But electromagnetism gets stronger up close. How does that work?
It's all about how the quantum vacuum reacts. In electromagnetism, you get virtual electron-positron pairs popping up around a charge. They kind of screen it, making it look weaker from far away.
Okay.
In QCD, you get virtual quark-antiquark pairs doing some screening too, but it's totally swamped by the effect of virtual gluons.
And because gluons carry color charge.
They don't screen, they anti-screen. They reinforce the central color charge. Imagine this, like a cloud of virtual gluons actually boosting the charge the closer you look. A thundercloud effect, some call it.
So the force actually gets weaker at tiny distances. That's weird.
It's fundamental to QCD. We talk about the strong coupling constant, alphas running, getting smaller at high energies or short distances. Discovering this in the 70s was huge. It solved theoretical problems, explained experimental results, and eventually won Gross, Wilczek, and Pulitzer the Nobel Prize in 2004.
And the practical upshot is we can actually probe inside protons, right?
Yeah.
At high energies, the quarks and gluons sort of ignore each other enough for us to see them.
Exactly. It makes the calculations possible.
Okay, and this ties into another point that just seems wrong intuitively. The origin of mass. You're saying the actual mass of the quarks in a proton or neutron. That's only like 1% of the total mass.
Yeah.
Where's the rest coming from?
This is one of the most profound consequences of QCD. The vast majority, like 99% of the mass of the ordinary matter around us, it isn't from the inherent mass of the quarks. It's an emergent property. It comes from the sheer energy tied up in the strong interaction. Yeah, the kinetic energy of these quarks and gluons zipping around like crazy, and the potential energy stored in that incredibly powerful gluon field holding them together. Remember, EMC1.
Wow. So energy equals mass. The binding energy is the mass.
For the most part, yes. The force that glues matter together is also what gives it most of its heft. It's quite something.
That really changes how you think about,
Yeah.
well, everything. Okay, so that was asymptotic freedom, weaker up close. What about the flip side? Color confinement.
Right, the logical consequence. If the force gets weaker at short distances, it must get stronger as you pull quarks apart, much stronger. Color confinement is the idea that you simply cannot isolate an individual quark or gluon. It's impossible.
Why impossible?
Because if you try to pull, say, a quark and a quark pair apart, the force between them doesn't drop off like gravity or electromagnetism. It stays roughly constant, about 10,000 newtons. Imagine pulling against that.
10,000 newtons, that's huge, like lifting a car.
And it doesn't decrease with distance. So to pull them infinitely far apart would take infinite energy, which you don't have.
So you literally can't pull a quark out of a proton. What happens if you try? If you pump in energy?
The energy you put into trying to separate them gets stored in the gluon field between them. It forms this kind of flux tube or string of energy. As you stretch it, the energy in the string increases and increases linearly with distance. Eventually, there's so much energy packed into that string that it becomes energetically cheaper for the vacuum itself to just pop, create a new quark-antiquark pair out of that energy.
Whoa.
The string snaps, but instead of free ends, you now have two strings, each ending on one of the new particles. You end up with two separate color-neutral hadrons instead of one.
So try to break the bond just. Makes more particles. You pull on the string, it breaks, but you just get two smaller strings, each with quarks on the end.
Exactly. That's called hadronization or string breaking. It's what particle physicists see as jet sprays of new hadrons coming out of collisions. You never, ever get a free quark.
That's incredible. The system refuses to be broken in that way.
It's fundamental. Now, interestingly, while we see this constantly in experiments, getting a rigorous mathematical proof of confinement directly from the equations of QCD is still one of the biggest unsolved problems in theoretical physics. A Millennium Prize problem, even.
We know it happens, we rely on it, but we can't quite prove it from first principles yet.
Okay.
So that's the quark-gluon bond. Intense, local, confining, creating mass. Now, let's switch gears completely. Quantum entanglement. This is the one Einstein called spooky action at a distance, right?
That's the one. And the crucial thing to grasp right away is that entanglement is not a force like the strong force. There's no particle exchange, no push or pull. It's a correlation, a holistic property of quantum states that are linked no matter how far apart they are.
Okay, not a force, but a connection. How is it defined, like, mathematically?
In the math, an entangled system's state, its wave function, cannot be described by just multiplying together the states of its individual parts. It's non-separable. The system has to be described as one single entity.
You can't describe particle A without implicitly describing particle B, even if they're light years apart.
Exactly. The classic example is having two particles, say electrons, created in a specific state called a spin singlet. In this state, their spins are perfectly anti-correlated. If you measure the spin of electron A along some axis and find its spin-up, you instantly know that electron B, wherever it is, will be measured as spin-down along that same axis.
Instantly. That's the spooky part, isn't it?
That's what bothered Einstein, Podolsky, and Rosen the EPR paradox. Before you measure, each particle is in a superposition. It's potentially both spin-up and spin-down. The act of measuring particle A seems to instantaneously collapse the wave function for the entire system, forcing particle B into a definite state faster than light could travel between them.
Which sounds like it violates relativity. Einstein thought there must be some hidden information, some hidden variables carried by the particles that predetermine the results all along, like matching gloves sent in separate boxes.
Right. But then came John Bell in the 1960s. He figured out a way to experimentally test this. He derived inequalities, Bell's theorem that set a limit on how strong these correlations could be if local hidden variables were the explanation.
And the experiments.
Over decades, countless experiments have been done, and they consistently violate Bell's inequalities. By a lot. The correlations are stronger than any local classical explanation can allow. Entanglement's non-local weirdness is real.
Okay, so the correlations are real and non-local. But if measuring one instantly affects the other, how is that not faster than light communication? Can't I use it to send signals?
Ah, the million-dollar question. The answer lies in the randomness. While your measurement does instantly determine the state of the distant particle, the outcome of your measurement is fundamentally random according to quantum
I
mechanics.
can't choose whether I get spin up or spin down.
Exactly. You can't force the outcome to send a 1 or a 0. You only discover the correlation after you and the person with the other particle compare notes, usually via some classical channel like a phone call or email, which is limited by the speed of light.
So no FTO communication. That's the no communication theorem. The correlation is real, but you can't use it to transmit information faster than light.
Correct. So it's better not to think of collapse as a physical thing spreading through space. It's more like an update of the information we have about the probabilities governing the entire system. It's inherently non-local information.
Okay, so let's really nail down the comparison then. We've got the Quark-Gluon bond and quantum entanglement. Two very different quantum beasts.
Fundamentally different, yes. Let's look at the mechanism. The Quark-Gluon bond is dynamic, it's happening constantly, mediated by gluons being exchanged back and forth. It's a physical interaction, local in space-time.
Right, whereas entanglement.
Entanglement is more static. It's a property of the shared state, the wave function. Once set up, there's no ongoing exchange needed to maintain the correlation. It's inherent to how the system is defined.
And spatially. Worlds apart, right?
Completely. The strong force is incredibly short range. We're talking femtometers, 10 eurometers, the size of a proton. Within that tiny range, its strength changes dramatically weak up close, strong at the edge. It lives in a very specific, localized region.
While entanglement is the definition of non-local, the equations don't care if the particles are nanometers or parsecs apart. Distance is irrelevant.
Utterly irrelevant to the correlation itself.
Okay, and they both involve a kind of inseparability, but it means totally different things.
Yes, absolutely crucial distinction. For quarks and gluons, it's physical confinement. You cannot physically pull one out. Trying to do so creates more particles. They are physically bound together.
But for entangled particles,
It's state non-separability. The particles themselves can be physically separated by vast distances, but the information about their state, their quantum properties, remains interdependent. You can't fully describe one without the other.
you can have the particles separate, but their fates are linked.
Got it. And there's actually an experiment that really drives this distinction home using top quarks.
Ah, yes, the top quark. It's fascinating. Top quarks are incredibly massive, the heaviest known fundamental particles. They decay extremely quick.
Oh, quick.
So fast, in about 10 seconds that they decay, before the strong force has time to confine them into hadrons through that whole string-breaking process. They don't have time to hadronize.
Okay, so they exist briefly, but not long enough to get trapped in the usual way.
Exactly. And experiments at the LHC, the Large Hadron Collider, have now measured quantum entanglement between pairs of top and anti-top quarks created in collisions with high precision.
So you can measure entanglement between these quarks even though they never get physically confined by the strong force? Precisely. It's clear, unambiguous proof that entanglement and color confinement are two totally distinct phenomena. Entanglement exists based on how the quarks were produced, completely separate from the subsequent, or in this case absent, effects of strong force confinement.
That's a fantastic experimental confirmation. Okay, so let's quickly recap the differences. Quark-Gluon bond. Physical force, gluon carriers, short range, physical confinement.
Right, and entanglement.
Mhm.
Non-local correlation, no force carrier, distance independent, state non-separability.
Interaction versus information, in a way.
That's a good way to think about it. One is about dynamics and force, the other about shared quantum information. Fundamentally different.
But here's where it gets really mind-bending, apparently. Despite being so different, these two areas are now starting to converge.
Yes, this is the really exciting cutting-edge stuff. Physicists are realizing that entanglement isn't just something you set up carefully in a lab with photons or electrons. It seems to be a crucial, fundamental feature inside the very matter held together by the strong force.
How so? Inside a proton, for example.
Exactly. We've known for a while that the simple three quarks picture of the proton is way too simple. Deep inside, it's this incredibly complex, dynamic soup.
The valence quarks, yeah, but also loads of virtual quark-antiquark pairs popping in and out of existence to see, and just countless gluons constantly interacting.
Right. And the new insight coming from applying ideas from quantum information science to QCD is that this whole complex system of partons, the quarks, antiquarks, and gluons inside the proton is actually in a state of maximal quantum entanglement.
Maximally entangled. Wow. How do you even measure that?
We can quantify it using a concept called entanglement entropy. And what's really striking is that researchers have found a direct mathematical link between this internal entanglement entropy and something called Shannon entropy, which measures the information or uncertainty in the distribution of the final particles produced when you smash protons together.
So the entanglement inside the proton dictates the information content of the debris outside after a collision.
That's the connection they've found, and it's been tested against data from experiments at accelerators like HERA and the LHC. It seems to hold up.
That feels like a huge shift. Those parton distribution functions, the PDFs, that tell us the probability of finding a quark with a certain momentum. We used to think of them as classical probabilities.
And now the thinking is evolving. It looks like these PDFs might actually be determined, or at least heavily constrained, by the underlying entanglement structure of the proton's constituents. Entanglement might be the organizing principle.
And the gluons play a key role in maintaining all this entanglement.
It seems so. The constant gluon interactions appear to be crucial for generating and sustaining this high degree of entanglement among all the partons.
Okay, so entanglement is woven into the very structure of the proton. What about dynamic processes like that hadronization, the string breaking thing?
That's another area where quantum information ideas are shedding new light. Hadronization, that process where the initial quarks and gluons turn into the jets of hadrons we actually detect, can be viewed as a complex quantum information process itself.
How does that work?
Well, imagine you start with an entangled quark-antiquark pair flying apart. The strong force pulls on them, the flux tube forms, energy increases, and new pairs are created from the vacuum. You end up with this complex, evolving, multi-particle entangled system. The transition from that initial state to the final observable hadrons looks very much like quantum decoherence.
Decoherence, where quantum states lose their coherence and start behaving more classically due to interaction with the environment.
Exactly. The initial entanglement between the first few partons gets spread out, or lost, into correlations among the much larger number of final state hadrons. The information is still there, just distributed differently.
And people are even modeling the Quark-Gluon plasma, that ultra-hot soup of free quarks and gluons from the early universe, using these ideas.
Yeah, describing the QGP as a kind of noisy quantum channel.
A noisy channel.
Meaning, as an initially entangled system, like a quark-antiquark pair produced in a collision, travels through the QGP, its interactions with the plasma cause errors, just like noise on a communication line. They talk about amplitude damping, which physically corresponds to jets losing energy, or jet quenching, and depolarizing noise, which corresponds to decoherence, messing up the initial entanglement patterns. It's a whole new language to describe these phenomena.
Fascinating. But it sounds like really understanding all this, especially the strong force in its most complex regime, the strong coupling regime where confinement happens. That's tough computationally.
Extremely tough. For classical supercomputers, yes. Simulating QCD accurately, especially things happening in real time or under extreme conditions, runs into massive computational walls. One big one is the notorious sign problem in methods like lattice QCD.
The sign problem makes simulations exponentially difficult.
Pretty much, for many important scenarios. It hinders our ability to calculate things precisely from first principles, but this is where quantum computing comes in.
Ah, the cavalry.
Potentially, yes. Quantum computers, by their very nature, operate using quantum mechanics. They are inherently suited to simulating other quantum systems, like QCD. And crucially, they don't suffer from the same sign problem that plagues classical methods.
So people are actually working on putting QCD onto quantum computers, mapping the fields and interactions onto qubits.
Absolutely. It's a very active and exciting area of research, mapping QCD onto qubits or even quadrats, developing algorithms. Early proof-of-principle simulations have already been done on small quantum devices. It's early days, but the potential is enormous.
What could we do with that kind of capability?
Imagine being able to actually simulate hadronization unfolding in real time, or calculating the properties of protons, neutrons, and other hadrons directly from QCD with unprecedented accuracy. Or probing the physics inside neutron stars, or understanding the Quark-Gluon plasma in detail, things that are currently beyond our reach.
That would be revolutionary. And maybe even tackle that confinement proof.
That's the ultimate dream for many. And there's an even deeper theoretical angle emerging, too, exploring the connection between the actual geometry of the strong force field, like that flux tube, and the information theoretic structure of entanglement.
Geometry and information linked.
Yes. Some recent theoretical work suggests that as the confining flux tube forms, the entanglement entropy actually changes in specific ways. The formation of the string seems linked to a suppression of quantum correlations, an increase in entropy.
Which hints that confinement itself might be deeply related to how quantum information behaves under the strong force.
It's a tantalizing hint. Could understanding the information flow finally give us that first principles explanation for why quarks are confined? It's a major driver for this research.
Okay, so let's try and wrap our heads around this. We started with two distinct phenomena: the quark-gluon bond, a physical force, local, strong, confining, the source of mass.
Right. And quantum entanglement, a non-local correlation, no force carrier, about shared information, state inseparability, independent of distance.
Totally different beasts, confirmed by experiments like the top quark one.
Yes. But now, the cutting edge is asking this really profound question. How does the force described by QCD generate and structure the entanglement we're now seeing is fundamental within matter?
It suggests maybe the old view of just particles and forces isn't the whole story. That quantum information and entanglement might be more fundamental, more central organizing principles than we thought.
That's the potential paradigm shift, yeah. It challenges us to think differently about what fundamental really means in physics.
Are forces just emergent consequences of how quantum information is allowed to flow and structure itself?
That's the big, speculative, but incredibly exciting question people are starting to ask. Are forces and entanglement maybe just two sides of the same, deeper coin, rooted in quantum information?
So, something for you, the listener, to ponder. What if the familiar forces shaping our universe, like the strong force binding nuclei together, are ultimately just expressions of underlying rules governing quantum information? Could forces and entanglement be inseparable aspects of a single information-based reality? Chew on that one.